Brief introduction, I'm Ben Marshall. I work at the National HVDC Centre here in Great Britain. We're part of SSE Transmission, which is part of the larger SSE. Within the National HVDC Centre, we have partners across both the ESO, our electricity system operator, and all of the onshore TOs, advising and informing and directing the priorities of the centre. The centre's objective is very much to de-risk the integration of converter technology onto the grid. So if we move to the next slide, Paul, is that possible? Yeah, so there's just a brief introduction of who we are and what we are. If we move to the next one. So what am I going to talk about? First and foremost, why do we need to discuss the environment of compliance testing? How has it changed, and why is that an area that we need to develop new processes and new approaches to? I will also go through our project development processes, explaining why the key development milestones of projects become important, particularly as you combine devices and start having to view compliance across the overall performance of the composite behaviours of those devices. I discuss how promotion informs this topic, and then I go through our experience of current practices that we investigated via a questionnaire and some gap analysis, and we provide key recommendations within the D11.5 report. So if we move to the next slide, purpose of compliance evaluation. Before getting into the nuts and bolts of this, it's always useful to step back and think about what is compliance for, what's it trying to deliver. So okay, it's a demonstration of performance. That much probably was obvious to most. It's providing a clear basis for the onshore network operation and development. That's important too, because the reason we have codes is to provide an envelope for the performance of the onshore grid, which provides a clear expectation to the user connecting to it as to how his performance should complement that grid. And in order to be comfortable that we can all plan and design our networks appropriately, we need to be comfortable that the performance of the user is again demonstrated robustly. So that's very much the clarity that we're looking for today. The responsibilities and duties across technical codes. So Christina fielded a question about whose responsibility is the gap. I guess my response would be, it depends on what the gap relates to, because the compliance processes are very much about defining the roles within the provision of voltage support or frequency regulation. It's important to understand where an individual vendor's duties stop and the TSO's responsibilities begin, and vice versa. Commercial market investment processes, very hard for a project to proceed into business as usual without a clear demonstration of its capabilities. Those in turn inform a variety of revenue streams. Most TSOs have processes which require the compliance evaluation as a key marker in the delivery of the project. So projects are not viable without this. And then I've put in red two other areas: providing effective data and modeling exchange, and verifying model performance against real-world testing references. And why have I put them in red and illustrated them like that? Well, much as if you had a builder building your patio, you might struggle to get a drawing of what he's done at the end of it, or after you've done your accounts, needing to go back through the paperwork if you're working with your manager, you might struggle to find all of that, because it's often the inconvenient aspect of the process, and it's the last thing that often is there on the checklist. So in natural behaviour, it's often the piece of work which is delayed or is related to a more limited data exchange. And so today, our data exchanges tend to revolve around the things that have been in the past important in managing our AC systems. So they tend to revolve around RMS level model exchange and validation and construction. They don't tend to respond to the changing needs of the system in more instantaneous modeling, which completely includes electromagnetic transient phenomena, such as a response to transient overvoltage or a response to the recovery from a fault ride-through event. We approximate that to what we know, which has been the behavior of a synchronous machine in a balanced fault, which is very different to the behavior of a converter. So these aspects, which have seemed like nice to have in the past, that's changing as we move to a converter-dominated environment. These nice to haves suddenly become essential. So if we move to the next slide, Paul. So just to put a bit of an environment spin on it. So I've got on the left there the GB environment. Within GB, by 2030, we will need to accommodate some 40 gigawatts of offshore wind across a variety of approaches, perhaps, that may not entirely be related to mesh, but some of it may be. We also have around 30 gigawatts of overall interconnector capacity expected over that same time frame. And again, some of that may be becoming a hybrid design, including some wind developments within it. So within that context, there may be developments across continental Europe, where the northwest of Europe develops out a North Sea grid to partially or entirely mesh the contributions of wind off its shores, and that in turn may integrate with the GB environment. Within all of this, there's no perfect solution. There are a number of challenges. So from a HVDC standpoint, we are transitioning from an environment of synchronous generators with inherent behaviors to, as Christine mentioned, much more complex control-based behaviors, which are based on current loops, and current loops can go wrong. So the HVDC risk slide there you see relates to the tracking of a PLL through a fault ride-through event, and how the tuning of that PLL would change its performance across different levels of system strength. The HVAC risk, which is a familiar one, relates to, sorry, it's going mad here.
Yeah, sorry.
Yeah, that's okay. If you wheel back one side, Cole, if you could. Yeah, that's great. The HVAC risk relates to small signal challenges associated with the resonances inherent in radial AC systems. And again, the inherent resonances within any current loop-based control system, and how they may combine, again, can disturb the onshore system, or indeed the vendor system of a large HVAC connected wind farm. I talk on the right here about the traditional compliance tests, which have been focused on the AC boundary. As Christina was mentioning, boundaries are important for compliance testing. You've got to clearly describe what you're trying to achieve. And in the past, it's been relatively straightforward to do so, because you've had an AC system to which you're connecting an AC network for the wind. And inherently, then you can translate an onshore AC test to a generic test offshore. If we move into the HVDC environment, then what we actually have is a control system, which is communicating data associated with the onshore AC disturbance, either via the control behavior of the HVDC or via signaling, which encourages a composite response of the HVDC and the wind. Or you get a sympathetic response from the wind from the HVDC's behavior. It's entirely a function of the overall control philosophy and control approach as to what you see onshore and how the performance relates to the individual devices. There's a divvying up of responsibility going on. And at the bottom, you can see the North Sea grid as postulated by promotion. And the question there is, well, what is compliance in that above discussion? Because now you have multiple points onshore. For any given fault onshore, let's say in the northwest of continental Europe, you will see a sympathetic reduction in voltage to other points in that network. So it's not just one point onshore which is seeing the effect of a fault, let's say. Equally offshore, you've got multiple points which can respond to that behavior and need to be resilient to it. So again, it's not about individual devices and individual responses to injection. It's about an overall philosophy of control, and that the devices involved in that are providing their attendant requirements in order to give the overall ability to survive the disturbance and provide the necessary performance. Very different world we're moving into. So if we move into the next slide, Paul, we have a number of technical risks emerging, and you can summarize these as risks of single point failures as network conditions change. This is because our controls, as I mentioned, are current focused. They are tracking the AC system. They are making assumptions about it. At certain points in time, those assumptions may not become valid. That might be against an operational condition that was unexpected, or it may be a scenario of events, a multiple fault event, such as the one in South Australia, which is shown in the topmost left example. Or it may be that there are particular sensitivities in relation to a voltage disturbance, as illustrated on the 9th of August event, which is in the top two right examples. And in these situations, there's a question about how you track them. How do you ensure that the tuning that you do at the point of commissioning is robust against the range of operational scenarios that may emerge? And how do you ensure, as the network changes, as it inevitably will, that that is maintained? There's a question about completeness of control. Incorrect or incomplete information around how controls track, how controls limit, how controls protect may mean that in an event there is a different behavior to anticipated. As controls are tuned and the network strength changes, the harmonics on the network shift more towards the fundamental, and a larger range of network related changes can influence the applicability of the tuning. You can also have hidden project behaviors. You can have controllers which are competing against each other. A converter is essentially a device with a current rating and not a current overload rating that is appreciable or of long duration. So if you're expecting a device to simultaneously respond to, let's say, a disturbance in both frequency and voltage, then it may struggle to do so. And there are examples in California of solar projects falling out as a result of lightning strikes because there was a simultaneous move away from the frequency bandwidth they were expecting. At the same time, there was a voltage disturbance. And so we've got to be guarded against the overall behaviors and make sure that the robustness of the controls is there. And these controls are very flexible. So whilst I've talked here about the risks, I also make the point that HVDC solutions can be part of the overall response to this. It need not be part of the problem. It's all a question about the robustness of the approach and the applicability of the compliance tests. So what do I mean by that? If we move into the next slide, Paul. So I'll just go through the project development side. Conscious of time, I'll speed up a bit. So if we talk about project life cycle, this is a typical life cycle for a HVDC device. It starts out with outline RMS analysis, informing the overall requirements. And then as you move into detailed design, increasingly a level of EMT analysis is conducted, often offline, often using programs like PSCAD, for example, or EMT-RV. We then move into a factory acceptance environment where we are well used to hardware being introduced into the loop and an RTDS framework being utilized as a testing platform for the real responses of a control and protection system to sample disturbances, which may inform a code and indeed compliance requirements based on those generic disturbances. That's a device focused approach. Now, as you move out of the factory, there may be further analysis that happens as you approach the point of commissioning, certain retunings occurring, and then you're into service. And again, there will be snagging, there will be software updates, there will be other revised tuning as sequentially the capacity is brought on stream. Now, the important point is that's just describing the HVDC side. A similar set of requirements exist for your turbines, for any STATCOMs that are involved in your connection, and you've got essentially multiple devices going through the sequence at multiple times with a different data resource available to them. At certain points, there will be more information, for example, on the characteristics of the cables. The the Seagray and Senelec processes describe 5 phases, which I've mapped onto this. But as you can see, there's not a perfect mapping. And again, this is because in the past we've had the luxury of AC systems where we've not had to think in too much detail about what information is developed at what times informing what tests. As we now move into a world where the entirety of the compliance performance is dominated by the control and protection responses of the converter and the turbines, we need to be much more mindful of what information we're using to base that upon. So if we move to the next slide, Paul. So how does promotion inform this? Well, promotion across a number of work streams has conducted demonstrations. So it's looked at the behaviors of different topologies. It's looked at the converter interaction with the turbine. It's looked at the protection concepts and indeed demonstrated the DCCBs and the IEDs associated with that protection system. And so we've conducted real world examples of performance. We've combined real-time investigation of physical elements within that, physical IEDs, for example, in our Work Package 9 demonstration, combining those with models as well. And we've validated those models. We've validated RS-CAD models against the devices themselves. So we've understood what a representative multiple system looks like. Move to the next slide, Paul, if we could. So within the promotion project, we have integrated within a multi-terminal environment a series of intelligent electronic devices which are conducting the equivalent of a AC protection relays action of discrimination and initiation of DC circuit breaker responses. We simulated the DC circuit breaker responses within that environment. We've tested a range of different fault locations and effectively looked at the characteristics of the DC fault upon that DC circuit. So we've taken both an analogous approach to an AC system environment, but we've equally subjected it to different scales of disturbance and tuning relative to different vendor approaches to the converter control philosophies. So we've looked at an environment which is entirely described by control behavior, and we've considered a variety of control behaviors against a variety of events. And I guess this gives you a bit of a feel for what the future might need to look like in terms of how we describe our standards. It's much more about describing an environment which is changing, and it's about focusing in on having the modeling and simulation capabilities to understand it. So if we move to the next slide. So there's been a number of other findings. I mean, Christine mentioned a few earlier. We've produced a requirement for meshed offshore grids, which has a series of requirements, and buried within that is indeed information exchange coordination. We also have wind power park compliance tests and revised approaches to those, and we've also explored the approach of DRU, approaches of connection of these offshore AC islands, and how the approach differs for those. So we've started to discuss the challenges and identify some of the issues. If we move on to current practices, so we sent a questionnaire around the various stakeholders, and thank you all for your responses. Just to highlight a few of the points. So in the top left here, you've got the fractions of requirements that are currently subject to simulations, which is the blue, or tests in the orange, during the 5 stages of the Seagray test schedule. So you can see here a relatively limited number of simulations and tests in the planning stage, and an increasing level of tests when we get to the operational stage. But I guess the interesting point here is that there is, across all parties, an inconsistency in behavior. There are different proportions of TSOs out there who are applying simulations and tests to this situation, and in different circumstances. So we all have a different history here. And I think the reason for that is often that we're in different stages of the journey towards converter integration, but equally we have access to different levels of understanding of the converters and ability to model them, which is quite critical. And so there's to coin a phrase from our friend Boris, there's a bit of a leveling up to be done here across this to ensure that we're all thinking in the same way about simulation aspects of compliance, so that we can all see the whole of the problem that we're engaging with, and we understand the effect of the tests we're doing upon the entirety of the devices responding to them. So if we move to the next slide, Paul, we had various pieces of feedback, and I guess I won't linger too much on them. You can do so at your leisure in the slide deck, but it's very much focused around how do we use EMT modeling? How do we validate it? How do we test it? How do we ensure that we're combining the appropriate aspects of that EMT environment behavior together to be comfortable that we're capturing the performance we're going to get? And equally, how do we monitor it? So I think we're all in that same world where we can see what the future looks like, but we're looking how to engage in it. If we move to the next slide, Paul. So just a quick bit on gap analysis. Now, hopefully these next two slides will really bring it home to people. So again, a lot in this slide. I guess the important thing to say is I describe here a potted view of where we are in terms of our analysis environment today. And that's very much grounded in economic and RMS tools to understand our broad onshore transmission requirements based on an inherent understanding of the dynamics of the plant that we're looking at. We do use EMT analysis, and to a certain extent, mainly in the factory acceptance environment, RTDS, as a validation exercise, mainly to have comfort on our RMS behaviours and to ensure against some fairly broad standards that we are not exceeding any particular limit in relation to transient phenomenon. But the inherent way in which our standards are described, we're anticipating that if we do everything right, we won't be. If we move to the future, which is the next slide, the world changes. And the world changes because if we take the example of the offshore AC grids, there's no inertia. There is a power system control response. There is no short circuit level that's inherent. There are controlled fast fault current injections during a disturbance, and there are speeds of response associated with reactive power delivery, which are dictating the strength of those networks. And onshore, the levels of inherent synchronous machine behavior are again reducing as greater contributions from converters arise. And what that means is no longer are you in an environment where you can fit your framework around inherent behaviors. You need to fit your framework of analysis around the modeled performance of control systems. You need to be comfortable that across a range of operational scenarios, those control systems combine and complement one another, and where they don't, damping solutions need to be defined. I've identified in the red the EMT areas that we continue to see, and so you can see a growth in those. But I guess the more significant growth from just one area of factory acceptance testing is the effect that this has on RTDS hardware in the loop, because fundamentally there is not just the gap in terms of process, there's a gap in information, and the gap of information relates to the IP associated with the converters and the devices more generally that are responding in these environments, and we need to close that. The only way to close that satisfactorily is with complete control understanding. That's what allows you to see the whole picture. That's what allows you to filter in on the areas of further analysis, and it also gives you the confidence that an offline model, which has maybe a simpler structure to it, is still capturing everything you need. So if we move to the next slide, Paul, promise we're close to the end now. So the gaps we've highlighted are information models and exchange, hardly surprising. We need to look at standards supporting interoperability. We need to be thinking about practical input and output tests, and we also need to look at that from a small signal perspective as well. We have commonly established models for looking at the needs for data that we need to develop. So how much of the network does a TSO need to exchange with a user? How much information does a user need to exchange with a TSO in order to give the compliance validations we currently have onshore. But there are new areas of testing that we also need to describe, and they relate to the offshore disturbances. As Christina noted, you've got a wider range of offshore behaviours going on, and across both the DC and the offshore AC circuits, very different dynamics defining them. So if we move to the next slide, key recommendations. Unsurprisingly, these are in the areas of modelling. It's in the areas of the compliance tests. So it's about making sure that we define the new tests, we redefine the existing tests to be relevant to these composite environments, and we ensure that we're getting the levels of data that we need in order to inform that analysis, because increasingly it's going to have to be simulation based. And I think that's it. Other than my closing remarks, I will leave this very short, just to say a favourite example I would give is the 15th century map that you see here of Italian sailors, which has a very good representation of the Mediterranean and a diminishingly good representation of everywhere else. We're in that environment at the moment with compliance testing. We understand the RMS and we understand how it relates onshore. As we move beyond that, we need to develop new and better understanding of the broader range of phenomena that we're seeing in more complex systems. And the only way to do that is by taking defined steps. So much as the Italian sailors stayed close to the coast until they were confident of their environment and went progressively offshore, we're in the same place. And I like this map because in the orange, you've got a sea monster, and there are challenges and risks, and there'll be dragons somewhere in all of this. But if we take a very defined and deliberate approach, we will get through it, and we need to work out from what we know towards what we don't. So that's it for me.
Thank you very much, Ben, for